Welcome, guys, to another session on dynamic programming. And today we are going to be discussing problem 6.6 multiplication operations and how to parenthesize to achieve a certain outcome. So, with that, let's dive in. So, to complete the problem statement, we are given the multiplication table for three elements, A, B, and C, which is given on this right side. And we are given a set of numbers S1 through Sn, and we have to apply parentheses in such a way that after multiplying using the parentheses operation, we get A as the outcome. Now, we cannot move the different numbers around S1 through Sn. We cannot move them around because the operation is neither commutative nor associative. So we can only place parentheses um, around these numbers, and that's pretty much all we can do. And just like matrix chain multiply, these numbers cannot be moved around because they are not commutative. And if S1 times S2 is not the same as S2 times S1, and therefore we have to keep everything exactly in order and just add those parentheses. So what is the idea behind this solution? And the idea behind this solution is very similar to the chain matrix multiply solution. Now, what we can do is we can define this new matrix Uij x, where this keeps the answers for uh, if we go from I through j, uh, then what is the possible outcomes? If you multiply, let's say, the subsection of this string I through j, so si through sj, and if you take all possible parentheses in that, that is x. So x is a list of all possible outputs by parenthesizing from this string from I through j. Also, uii of x is trivial, and if you go from I to I, then that si is the answer, and that's the only outcome. So given these two things, we can now construct a solution very similar to the chain matrix multiply. We know that every single element result is the same as Si. Then we start to build every pair. And every pair is essentially just look up through this table because a pair is just two elements. So the outcome has to be bound by this table. Then we move to every three tuple possible. And when you go to every three tuple, let's say from 1 to 3, if you were to multiply S1, S2, and S3, you could multiply S1 with S2, S3, or S1, S2 with S3. So there's two possible parenthesis outcomes. And so we will construct this three tuple result from every every pair result. So each solution builds from the previous solution. Because we knew the single element, we could build every pair. And because we know every pair and single element outcomes, we can build three tuples, and so on, till we reach the n tuple, which would cover the whole string S1 through Sn, and then we would know every possible outcome of parenthesizing this string. So here's a visual of the solution that we just described. Now, first we compute the trivial solution, which is if you go from 1 to 1, the outcome is Si. So these are indices on the string S. And if you're going from 1 to 1, that is S1. If you're going from 2 to 2, that's S2, and so on. So this diagonal is the trivial solution. Next, we compute every pair. And when you compute every pair, that's the next diagonal shifted from the main diagonal up. And in this, if you look at the first element is U1, 2. And if you do U1, 2, then U1, 2 is essentially all possible outcomes of 1 and 2. And we said pairwise is, if you go back, pairwise is essentially just this table, because you multiply one element by another element, you can map it using this table. So now coming back to this, each element here is easy to determine because let's say S1, 2. So you look at S1 and 2, there's only one possible way to multiply that. You just look up in the table. This one is S2, 3, and S2, 3 is again S2 times S3. S3, 4 is S3 times S4, and so on. So this diagonal is fairly easy to accomplish. When we get to the next elements, it gets a little bit more complicated. And just like chain matrix multiply, and if you haven't seen that, I would highly recommend you go look at my chain matrix multiply video. But when you get to three tuple has two possible outcomes. For example, if you look at S13, S13 is right here, and S13 can be done in two ways. Either it'll be S1 times S2 S3 or S1 S2 times S3. And those results can be composed from these two diagonals that are there before you. So by composing every three tuple in this diagonal above, you need to use the problems defined here before. And so once you have computed the three tuple here in this next diagonal row, then you move on to the four tuple, the five tuple, and the six tuple. And in this example, the six tuple is the final solution, and therefore once you reach S16 and you have computed every possible outcome of S16, that is the answer. Now a quick word on computing the S13. Keep in mind that when you multiply these lists, so if we go back to our original description, this X is actually a list. And so when you go from I through J, you know that there are multiple possible ways to parenthesize, unlike the chain matrix multiply where you only have one minimum or maximum possible value. Here, multiple values are possible. So we are keeping a list for I through J. And when you get to the three tuple, if you multiply the left side by the right side, then keep in mind that when you're multiplying the S13, the S13 can be made from S12, which is this element, or S23, which is this element, multiplied by a single element. So S12 multiplied by S3 and S23 multiplied by S2. So, and this matrix is actually representing Uij. So, in a sense, when you multiply these lists, this X is a list, this is a list. So these are two lists. And when we multiply elements with these lists, it produces other lists. So these lists continue to get multiplied. Now, the key important point to observe is that these lists would never grow bigger than size 3 because the end result of multiplying any of these numbers has to produce an outcome A, B, or C. So before we understand the order of this solution, we have to appreciate the fact that even though these are lists, the outcome of multiplying any two lists never exceeds the size 3 because the net result of multiplying these maps back to A, B, or C. Now, with that said, let's now analyze the order of this dynamic programming solution. Now, since we are computing this upper end of the diagonal of this matrix, and you have n elements here and n elements on this side, the order is really n squared over 2. So the order is n squared. But keep in mind that when we go from, let's say, 1 to 6, when you compute this element, you have to take every possible outcome by moving from by dividing the S1 through 6 as S1 multiplied by S5 through 6, or S1 S2 multiplied by S3 through 6, and so on. Just like chain matrix multiply, when you're computing this element, you have to move the pointer to slice this in n possible ways. And so you have this another factor of n that slices the range Sij, and therefore you get order n cube. So that is the solution to this problem. This problem resembles chain matrix multiply very heavily. The only difference is that we do not want to find the minimum multiplication operations. We want to find all possible multiplication outcomes, and in this case we are keeping them as lists instead of one single number. And eventually when we go across these diagonals, computing diagonally across, we reach this final value here, and S1 through n, and that value is the solution, and the solution can be computed in order n cube. Another important part of the solution was the realization that the multiplication of any of these two lists results in a list that is also of size 3. So the multiplication of any two lists never exceeds size 3. And with that, we conclude this solution, and hopefully you enjoyed this video. And if you did, please subscribe to this channel, and I'll bring you more dynamic programming solutions. And until next time, bye bye.